Hello there, and welcome to the Dreamy Sleepy Science channel. I'm so glad you're here tonight. Maybe you've had a long day. Your mind is still turning with thoughts, worries, lists of things undone. Maybe you're simply curious, seeking something gentle to carry you towards sleep. Whatever brought you here, you're welcome. Tonight, we're going to drift through the Milky Way, our home galaxy, exploring its quiet wonders, its ancient mysteries, its patient, luminous beauty. There's no test at the end. No need to remember anything. These facts are here simply to occupy your mind with something vast and peaceful, something that puts the smallness of our worries into perspective. The Milky Way has been turning for billions of years. It will continue long after we're gone. There's something deeply soothing in that thought. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Let your body settle into whatever position feels most comfortable. Feel the weight of your head against the pillow. Notice your breath, soft and steady. There's nothing you need to do now but listen, and even listening requires so little. You can let the words wash over you like starlight, gentle, distant, asking nothing in return. Now, let's begin our journey through the quiet cosmos of home. Our galaxy formed in the early universe not long after the Big Bang itself. When you look at the Milky Way or imagine its spiral arms stretching across space, you're looking at something nearly as old as time itself. It emerged from clouds of hydrogen and helium, gravity pulling matter together into the first stars. Those earliest stars have long since died, but their light once illuminated a younger, stranger cosmos. The galaxy you're part of tonight has witnessed almost the entire history of the universe. It remembers what we can only imagine. Think of all the time contained in that number, 13.6 billion years. Entire generations of stars have been born, have lived, and have died in that span. Mountains have risen and fallen on countless worlds. And through it all, the galaxy has turned, patient and unhurried, indifferent to the brief flickers of individual lives. Even now, as you rest in this moment, the galaxy continues its ancient rotation, carrying you along with it through the dark. The Milky Way contains between 100 and 400 billion stars. No one knows the exact number. It's impossible to count them all. But somewhere in that vast range, hundreds of billions of suns, exists every star you've ever seen with your naked eye, every star that's ever guided a ship or inspired a story or witnessed a human moment. Most of these stars are far smaller and dimmer than our sun, red dwarfs, burning slowly, barely glowing. They'll outlive our sun by trillions of years, still shining long after the last human thought has faded. Some stars are giants, bloated and dying, their light fierce and brief, and scattered among them are stars like our sun, middle-aged, stable, perhaps home to worlds of their own. You are made of elements forged inside some of those ancient stars. The iron in your blood, the calcium in your bones, these came from stellar cores, released when those stars exploded in supernovae billions of years ago. The galaxy recycles itself endlessly this way. Each of those hundreds of billions of stars has its own story, its own lifespan, its own slow journey through space. And here you are, on a planet orbiting one of them, drifting towards sleep under a sky full of its siblings. The Milky Way is shaped like a spiral with a bar through its center. If you could somehow leave the galaxy and look back at it from a great distance, you'd see a luminous disk with graceful spiral arms curving outward from a bright central bar. The arms are studded with blue-white regions where new stars are forming, interspersed with darker lanes of dust. This shape isn't static. The spiral arms aren't solid structures but density waves, regions where stars and gas bunch up temporarily before moving on. It's like a traffic jam on a cosmic highway, where the jam itself moves slower than the cars passing through it. The central bar rotates more slowly than the outer disk, creating a gentle shearing motion that helps trigger star formation. Material flows along the bar toward the galaxy's heart, feeding the supermassive black hole that lurks there. But we'll come to that in time. From our position inside the galaxy, we can't see this grand structure directly. We see it edge on, as a band of light stretching across our night sky. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. We're inside the very thing we're trying to understand, like someone trying to picture a forest while standing among the trees. Somewhere out there, maybe someone on a world orbiting another star is also looking up, also wondering about the shape of home. Our solar system orbits the galaxy's center at about 514,000 miles per hour. That's roughly 828,000 kilometers per hour if you prefer metric. Yet you feel none of it. No wind in your face, no sense of motion. You're moving at this tremendous speed right now. As you lie here, as your breath slows, as your thoughts begin to soften. At this velocity, it takes our solar system about 225 to 250 million years to complete one full orbit around the galactic center. Astronomers call this period a cosmic year or galactic year. The last time Earth was at this exact position in its orbit around the galaxy, dinosaurs were beginning their rise to dominance. Since the solar system formed 4.6 billion years ago, it has completed only about 20 orbits of the galaxy. 20 times around, through clouds of gas and past neighboring stars, through spiral arms and out again into quieter regions. The galaxy is so vast that even at 500,000 miles per hour, journeys take hundreds of millions of years. Speed and scale interact in strange ways out here. Fast becomes slow. Vast becomes intimate when you realize you're part of it. You're traveling through space at incomprehensible speeds. Yet here you are, perfectly still, safe and warm, ready to sleep. The Milky Way's disk is about 100,000 light-years across. A light-year is the distance light travels in 1 year, about 5.8 trillion miles, or 9.5 trillion kilometers. So the galaxy's diameter is about 580 quadrillion miles across. The numbers stop meaning much at this scale. They become almost like poetry, gesturing at something too large for the human mind to fully grasp. If you wanted to cross the galaxy at the speed of light, the fastest speed possible, it would take you 100,000 years. But of course, you can't travel at light speed. Even our fastest spacecraft would take billions of years to make the journey. The galaxy's size ensures a kind of permanence, a separation. Most of its stars will never know about most of the others. And yet light crosses these distances. Photons that left a star on the far side of the galaxy when humans were still learning to walk upright might be arriving at Earth tonight, might be falling on your rooftop right now, though too faint for your eyes to detect. The thickness of the disk varies, about 1,000 light-years in the thin disk where most stars live, perhaps 10,000 light-years if you include the puffier thick disk and halo. We live in a flat structure, like a plate or a coin spinning slowly in space. It's a comfortable thought, in a way, that even something as vast as a galaxy has a shape you can picture, edges you can imagine reaching, even if you never could. Our solar system sits about 26,000 light-years from the galactic center. We're not in the center, where things are crowded and chaotic. We're not in the outer halo, where stars are sparse and ancient. We're in what you might call the suburbs, a relatively quiet neighborhood in one of the spiral arms. More precisely, we're in the Orion Arm, also called the Orion Spur, a minor arm or partial arm between two major spiral arms. It's a peaceful location, far from the violent center but not too isolated. Just right, perhaps, for life to emerge and evolve undisturbed for billions of years. From this distance, the galactic center appears as a bright, hazy region in the constellation Sagittarius, visible on summer nights if you're far from city lights. You can't see the black hole at its heart with your eyes, but you can see the glow of millions of stars clustered densely around it. 26,000 light-years. The light you'd see if you looked toward the center left there 26,000 years ago, when humans were still hunter-gatherers, when no cities existed, when the world was younger and emptier and wilder. The galaxy shows us its past, always, because even light takes time to travel. We are here in this specific place, this cosmic address, neither too close nor too far from the action. And it's a good place to be. At the center of the Milky Way lurks a supermassive black hole called Sagittarius A star. It contains about 4.3 million times the mass of our Sun, all compressed into a region smaller than Mercury's orbit. The asterisk in its name is pronounced A star, a term from radio astronomy where it was first detected as a bright radio source. This black hole sits quietly at the galaxy's heart, anchoring everything with its gravity. Most of the time, it's relatively calm, not actively feeding. But occasionally, gas or even a star wanders too close, and the black hole tears it apart, superheating the material as it spirals inward. For a brief time, the center of the galaxy flares brilliantly. Despite its immense mass, Sagittarius A asterisk is invisible. Black holes don't emit light, they trap it. What we detect is the glow of material around it and the motion of stars orbiting it at incredible speeds. Some of those stars whip around the black hole in just years or decades, traveling at a significant fraction of light speed. It's strange to think that the gravitational heart of our galaxy is a place where nothing, not matter, not light, not information, can ever escape. A cosmic drain that time and space fall into. And yet, far enough away, its influence is gentle, benevolent even, holding the galaxy together. You're orbiting it right now, distantly, safely, the black hole at the center of home. The Milky Way is surrounded by a halo of dark matter. Most of the galaxy's mass isn't in stars or gas or dust. It's in something we can't see, can't touch, can't detect except through its gravitational effects. This invisible material extends far beyond the visible disk, forming a roughly spherical halo that dwarfs the galaxy we see. Without dark matter, the galaxy shouldn't hold together. The outer stars orbit too fast for the visible mass alone to contain them. They should fling off into intergalactic space. But they don't. Something is holding them in place, and we call that something dark matter. We don't know what it's made of. Not normal atoms. Not any particle in the standard model of physics. Something else. Something that pervades the universe, accounting for most of its mass, yet passing through ordinary matter like a ghost. You're moving through dark matter right now. It's all around you, undetectable, silent. There's something almost comforting about this cosmic mystery. The universe keeps secrets. Not everything is known or knowable. The galaxy floats in an invisible sea, held together by forces we're still learning to understand. Perhaps as you drift towards sleep, you can imagine yourself held gently by forces you can't see. Gravity, the bonds of matter, the chemical processes that sustain your life, the invisible web that connects all things. The Milky Way is colliding with another galaxy. Right now, as you rest here, our galaxy is in the early stages of a merger with the Sagittarius dwarf elliptical galaxy. This smaller galaxy has been orbiting the Milky Way for billions of years, and our gravity is slowly tearing it apart. Each time the Sagittarius dwarf swings through the Milky Way's disk, it loses more stars, more gas. These stolen materials are stretched into long streams that wrap around our galaxy like ribbons. Eventually, maybe already, there won't be a separate Sagittarius dwarf anymore. It will be fully absorbed, its stars becoming our stars, its identity lost in the merger. This isn't a collision in the violent sense. Galaxies are mostly empty space. Stars almost never hit each other during galactic mergers. Instead, they pass by like ghosts interpenetrating, their orbits gradually reshuffled by gravity until the two systems become one. The Milky Way has done this before, consuming many smaller galaxies over its history. Each absorption adds new stars, new material, new orbital patterns. The galaxy grows through gentle cannibalism, a process as natural as rivers flowing into the sea. And someday, something similar will happen on a grander scale. But we'll come to that story later. For now, just know that even galaxies are not eternal and unchanging. They evolve, merge, grow. Everything in the universe is in motion, even the things that seem permanent. The oldest stars in the Milky Way are about 13.2 billion years old. These ancient stars formed when the galaxy was young, when the universe itself was only a few hundred million years old. They're scattered through the galactic halo and in globular clusters, dense spheres of stars that orbit the galaxy's center like a swarm of bees around a hive. These old stars are metal poor, as astronomers say. In astronomy, metal means any element heavier than helium, and these stars have very few such elements. They were born from nearly pure hydrogen and helium, the primordial material left over from the Big Bang. The heavier elements hadn't been created yet. Subsequent generations of stars have been increasingly metal-rich, enriched by the deaths of previous stars. Our sun is relatively metal-rich, born from gas that had been processed through many stellar generations. We're made of recycled star stuff, third or fourth or 10th generation material. Those ancient stars are dim and red now, burning their fuel so slowly they've barely changed in all the eons since they formed. They'll continue shining for trillions of years more. In a sense, they're nearly immortal. They'll outlive our sun, outlive the galaxy's current structure, outlive almost everything except perhaps the universe itself. Somewhere up there, in the darkness beyond darkness, those ancient stars are still glowing, carrying memories of a younger cosmos, silent witnesses to time. New stars are still being born in the Milky Way. The galaxy isn't static or dead. It's a living system, continuously creating new stars from clouds of gas and dust. In regions called stellar nurseries, dense pockets within giant molecular clouds, gravity causes gas to collapse, heating up until nuclear fusion ignites and a new star is born. The Milky Way produces about 1 to 3 new stars per year, depending on whose estimate you trust. That might not sound like much, but over millions of years, it adds up. Right now, somewhere in the galaxy, a star is being born. Its light is just beginning its journey into space. Many of these newborn stars form in clusters, dozens or hundreds igniting together from the same cloud. Eventually, most will drift apart, scattered by the galaxy's tides. But for a while, they're siblings, stars of the same age and composition, sharing a common origin. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one of the closest stellar nurseries to Earth, about 1,350 light-years away. Through a telescope, you can see baby stars embedded in glowing gas, still swaddled in the material from which they formed. Creation continues. The universe isn't finished. Even now, new lights are dawning. The space between stars is not empty. Even in the void between solar systems, there's material, just not very much. The interstellar medium, as it's called, contains about 1 atom per cubic centimeter on average. That's a vacuum far better than anything we can create on Earth. Yet spread across the vast distances of space, it adds up to enormous total mass. This diffuse material is mostly hydrogen, with some helium and traces of heavier elements. Some of it exists as individual atoms, some as molecules, some as grains of dust no bigger than smoke particles. It's cold out there, just a few degrees above absolute zero in most places. In some regions, the interstellar medium clumps into molecular clouds, dense enough, by cosmic standards, to block light and provide the raw material for new stars. In other regions, it's thinner, nearly transparent. And in the hot, tenuous gas that fills the space between spiral arms, it can reach temperatures of millions of degrees, heated by supernova explosions and stellar winds. Even the emptiest space has texture and structure. Even nothing is something barely. The galaxy is permeated by this thin material, and light passing through it gets subtly affected, scattered, absorbed, reddened. You might think of space as a perfect vacuum, but it's more like a very, very thin mist. And we float through it, this near-nothingness, which somehow adds up to most of the visible matter in the galaxy. The Milky Way has at least 150 known globular clusters. These are ancient, densely packed spheres of stars, each containing hundreds of thousands to millions of stars in a region only tens of light years across. If you lived on a planet in the core of a globular cluster, your night sky would be brilliant, thousands of stars brighter than Venus crowding the heavens. Globular clusters orbit the galaxy in elliptical paths, spending most of their time far above or below the disk, plunging through it only occasionally. They're relics from the galaxy's youth, formed in the first billion years or so of its existence. The stars in globular clusters are all roughly the same age, ancient, and they orbit each other in a gravitationally bound swarm. The cluster as a whole is stable, held together by the collective gravity of all its stars. But individual stars occasionally escape, given enough close encounters with their neighbors. Seen from Earth with a small telescope, globular clusters appear as fuzzy spheres of light. Larger telescopes can resolve the individual stars, revealing the cluster's dense core and more diffuse outer regions. They're among the most beautiful objects in the night sky. These clusters remind us that stars don't always live alone. Sometimes they gather together, their fates intertwined, their light mingled. Company in the cosmic dark. The Milky Way's spiral arms are not permanent structures. They come and go, form and dissolve over hundreds of millions of years. What we see as spiral arms are actually density waves, regions where stars and gas temporarily bunch up due to gravitational perturbations, much like sound waves or ocean waves. As material moves through a spiral arm, it gets compressed, which can trigger star formation. That's why spiral arms appear bright and blue. They're full of young, massive, short-lived stars. These stars are so short-lived that they never make it out of the spiral arm before they die. They're born, live briefly, and explode as supernovae, all within the arm's borders. The Sun and other longer-lived stars, by contrast, drift in and out of spiral arms during their orbits around the galaxy. Our solar system has likely passed through spiral arms multiple times since it formed. Some scientists have speculated that these passages might have subtle effects on Earth, perhaps triggering ice ages or influencing the rate of cosmic ray bombardment. But the evidence is unclear. The spiral pattern itself rotates at a different speed than the stars, which is why stars can pass through it. It's like a pattern on a spinning wheel. The pattern and the wheel turn at different rates. There's something ephemeral and beautiful about this. Even the grand structures of galaxies are transient in the long run. Nothing stays the same forever. The Milky Way has eaten many smaller galaxies. Our galaxy is a cannibal, though a slow and patient one. Over billions of years, the Milky Way's gravity has captured and absorbed dozens of dwarf galaxies that wandered too close. These smaller galaxies are stretched into long streams of stars as they're torn apart, their material eventually mixing into the Milky Way's disk and halo. We can still see evidence of some of these ancient meals. Streams of stars with unusual orbits, moving in directions that don't match the galaxy's main rotation. These are the remnants of disrupted dwarf galaxies, ghosts of smaller systems that no longer exist as independent entities. The process is ongoing. The Sagittarius dwarf elliptical galaxy, as mentioned earlier, is currently being consumed. The Magellanic Clouds, two small irregular galaxies visible from the southern hemisphere, are also likely doomed to be absorbed by the Milky Way eventually, though it might take a few billion years. This is how large galaxies grow. They're built from the accumulation of smaller systems, merged together over cosmic time. The Milky Way contains stars from dozens of different ancestral galaxies, each with its own origin story, now all mixed together into one large system. It's a reminder that even galaxies have histories, lineages, family trees of sorts. The Milky Way is not a single pure entity but a blend, a mixture, a community of different origins. Some stars in the Milky Way orbit backward. Most stars orbit the galactic center in the same direction as the galaxy's overall rotation. But some stars, especially in the outer halo, move in retrograde, orbiting opposite to the main flow. These stars stick out like salmon swimming upstream in a river. Almost certainly, these retrograde stars came from dwarf galaxies that were absorbed by the Milky Way. When a small galaxy falls into a larger one, its stars retain their original orbital directions, which may be opposite to the new host galaxy's rotation. Over time, these stars get scattered, but their retrograde motion persists, marking them as foreigners, immigrants from destroyed systems. There's something poignant about this. A star's orbit contains its history, where it came from, what galaxy it called home before that home was consumed. The Milky Way stars don't all share a common past. Some are natives born here. Others are refugees from lost galaxies, now indistinguishable except for their unusual orbits. Even in a galaxy, there are outsiders, wanderers, stars that don't quite fit the pattern. And they're accepted all the same, bound by gravity if not by origin. You might think of your own thoughts that way as you drift towards sleep. Some moving with the flow, others circling back, all of them part of the same mind. The Milky Way's disk is warped. If you could view the galaxy edge-on, you'd notice that the disk isn't perfectly flat. Its outer regions are bent, warped upward on one side and downward on the other, like the brim of a hat that's been sat on. This warping is likely caused by gravitational interactions with nearby dwarf galaxies, especially the Magellanic Clouds. As they orbit the Milky Way, their gravity tugs on the disk's outer edges, bending it out of plane. There may also be contributions from dark matter structures in the galactic halo, pulling things askew. The warp isn't static. It appears to rotate, like a wave propagating through the disk. Measuring this warp precisely is challenging because we're inside the disk, trying to map its three-dimensional shape from within. But data from satellites like Gaia, which precisely measure the positions and motions of millions of stars, have revealed the warp's extent and structure. It's humbling, in a way, Even something as grand as a galaxy isn't perfect. It's lumpy, warped, asymmetrical, shaped by history and interaction, bearing the scars of past collisions and the influence of invisible companions. Nothing in the universe is geometrically perfect. Everything is a little bent, a little scarred, and maybe that's part of what makes it beautiful. There's a vast bubble of hot gas above and below the galactic disk. These structures, called the Fermi bubbles after the space telescope that discovered them, extend about 25,000 light-years above and below the galactic center. They're filled with high-energy gas and cosmic rays, glowing in gamma-ray wavelengths invisible to the human eye. No one is entirely sure what created these bubbles. The leading theory suggests they're the aftermath of a massive burst of star formation or a period of intense activity by the supermassive black hole at the galaxy's center, perhaps 10 to 20 million years ago. Some event released a tremendous amount of energy, blowing hot gas outward like a cosmic exhale. The bubbles are still expanding, pushing into the intergalactic medium beyond the galaxy. They're like ancient wounds or scars, evidence of some violent event in the Milky Way's recent past. Recent on cosmic timescales, anyway. If you were a gamma-ray sensitive creature living above the galactic plane, you'd see these bubbles glowing intensely, dominating the sky. But in visible light, they're nearly invisible, a hidden structure revealed only by our instruments. The galaxy has secrets, structure we can't see with our eyes, layers of reality existing just beyond our perception, visible only to those who know how to look. The Milky Way is moving through space at about 1.3 million miles per hour. It's not just the stars within the galaxy that are moving. The galaxy itself is in motion, falling through space along with other galaxies in our local group. All of us, Milky Way, Andromeda, and the smaller galaxies, are being pulled toward a distant region of space called the Great Attractor. The Great Attractor is a gravitational anomaly, a region of space where an enormous concentration of mass, perhaps clusters of galaxies hidden behind the Milky Way's disk, is drawing in everything around it. We can't see it directly because it lies behind the zone of avoidance, where the Milky Way's disk blocks our view of distant space. But we can measure its pull. The Milky Way is moving toward it, along with thousands of other galaxies, all participating in a vast cosmic flow that spans hundreds of millions of light-years. And beyond the Great Attractor, there's an even larger structure called the Shapley supercluster, adding its gravity to the pull. So the galaxy isn't just spinning in place. It's falling towards something, drawn by gravity across unimaginable distances, and carrying you with it, a passenger on a cosmic journey you never chose but are part of nonetheless. All this motion, and yet you feel only stillness, only the soft weight of your body against the bed, the quiet rhythm of your breathing. Most of the Milky Way stars are red dwarfs. These small, dim stars make up about 70% of all the stars in the galaxy. Each one is less than half the Sun's mass, some as little as 8% the Sun's mass, barely massive enough to sustain fusion. They're cool and red, emitting most of their light in the infrared. Red dwarfs burn their hydrogen fuel incredibly slowly. While the Sun will last about 10 billion years, a red dwarf can burn for trillions of years. Not a single red dwarf that has ever formed has yet reached the end of its life. The universe is too young. They're all still on their main sequence, still steadily fusing hydrogen, still shining. This means that long after the Sun dies, long after all the massive stars have exploded or collapsed, long after the galaxy has changed beyond recognition, the red dwarfs will still be glowing. In the distant future, they'll be the last stars left, flickering dimly in an ever-expanding, cooling universe. Most red dwarfs are too faint to see with the naked eye, even though they're far more numerous than stars like the Sun. The nearest star to Earth, Proxima Centauri, is a red dwarf. At just 4.2 light-years away, it's still invisible without a telescope. The galaxy is full of these quiet, patient stars, small, dim, but enduring. They don't blaze brilliantly like giants or supergiants. They simply persist, decade after decade, eon after eon, outlasting almost everything. The Milky Way contains vast clouds of molecules. These giant molecular clouds are the coldest, densest parts of the interstellar medium, with temperatures as low as 10 Kelvin, about -263 degrees Celsius. They're composed mostly of molecular hydrogen, along with carbon monoxide, ammonia, water vapor, and dozens of other molecules. Some of these clouds are enormous, hundreds of light-years across, containing enough material to form millions of stars. They're the sites of star formation, the nurseries where new solar systems are born. The densest cores within these clouds collapse under their own gravity, fragmenting into smaller clumps that each become a new star. Inside these clouds, it's dark. Dust grains block all visible light, making the interiors utterly opaque. If you were inside one, you'd see no stars, no light, just absolute darkness, colder than the coldest winter night on Earth. But radio telescopes can peer inside, detecting the faint emissions from molecules. And what they reveal is surprising. These clouds have structure, filaments, cores, shells. They're dynamic, turbulent, shaped by magnetic fields and the pressure of radiation from nearby stars. These clouds are where chemistry happens in space. Protected from harsh radiation, molecules can form and persist. Complex organic molecules, the building blocks of life, have been detected in some molecular clouds. The ingredients for life exist out there, floating in the dark between the stars. The Milky Way has satellite galaxies. At least 60 smaller galaxies orbit the Milky Way, most of them dwarf galaxies containing only a few million to a few billion stars. They're like moons to our planet, smaller companions bound by gravity. The largest and most famous are the Large and Small Magellanic Clouds, visible as fuzzy patches in the southern sky. They're irregular dwarf galaxies, roughly 160,000 and 200,000 light-years away, respectively. Many of the others are so small and dim they were only discovered in recent decades, revealed by careful surveys that picked out their stars against the background of the Milky Way. Some of these satellite galaxies are gradually being torn apart by the Milky Way's tides. Long streams of stars trail behind them, breadcrumbs marking their slow spiral inward toward destruction. Others are more stable, orbiting at greater distances where the Milky Way's pull is gentler. These satellites are important for understanding how galaxies form and evolve. The Milky Way likely formed in part by accreting smaller systems like these, and studying them gives us insight into dark matter, because even tiny dwarf galaxies contain far more dark matter than visible matter. The galaxy isn't alone. It has family, companions, smaller systems bound to it by gravity and history. A cosmic community, each member influencing the others in subtle ways. Light from the galactic center takes 26,000 years to reach us. When you look towards Sagittarius on a summer night, the light entering your eyes left the galactic center 26,000 years ago. You're seeing the past always because light has a finite speed and space is vast. 26,000 years ago, humans were hunter-gatherers. The last ice age was beginning. Neanderthals still walked the earth alongside our ancestors. None of our civilizations existed. No cities, no writing, no nations. And the light that left the galactic center back then, radiated by stars that may no longer exist, is just now arriving, falling on your rooftop, entering your eyes if you bothered to look. The galaxy reveals itself to us slowly, one ancient photon at a time. This is true of everything in space. The farther you look, the farther back in time you see. The universe is a time machine, showing us its history by virtue of light's finite speed. We can never see the galaxy as it is now, only as it was long ago. There's a strange comfort in this. The past is still arriving, still making itself known. Time is layered, folded, complicated. As you lie here in the present moment, photons from ancient times are washing over you, mixing past and present in ways that blur the distinction. The Milky Way's magnetic field is complex and tangled. Like Earth, the galaxy has a magnetic field, though far weaker and more complicated. This field threads through the interstellar medium, aligning dust grains, guiding cosmic rays, and influencing the motion of charged particles. Mapping the galaxy's magnetic field is challenging. It's invisible, detectable only through subtle effects on light and on the motion of particles. But over the past few decades, astronomers have pieced together a picture of a field that follows the spiral arms, loops around the galactic center, and extends into the halo. The field is generated by the motion of charged particles, mostly electrons in the hot ionized gas that permeates space. As the galaxy rotates, it winds up the magnetic field lines, creating a complex, tangled structure that changes over time. This magnetic field plays a role in star formation, helping to support giant molecular clouds against collapse until they're dense enough to form stars. It also confines cosmic rays, keeping high-energy particles from escaping the galaxy immediately. Even a galaxy has invisible architecture, fields and forces that shape its structure and behavior. Nothing exists in isolation. Everything influences everything else through a web of interactions, seen and unseen. Some stars have been ejected from the Milky Way entirely. These are called hypervelocity stars, and they're moving fast enough to escape the galaxy's gravity, speeds of 1,000 kilometers per second or more. They're rare, but a few dozen have been identified, racing outward into intergalactic space. Most hypervelocity stars likely gained their speed through interactions with the supermassive black hole at the galactic center. If a binary star system wanders too close, the black hole's gravity can rip the pair apart, capturing one star in a tight orbit while flinging the other outward at tremendous speed. Other hypervelocity stars may have been ejected by supernova explosions in binary systems, or by close encounters between multiple stars in dense clusters. Whatever their origin, these stars are now on one-way journeys into the void between galaxies. Imagine being on a planet orbiting one of these runaway stars. Your sun would be speeding away from the galaxy, and over millions of years, the Milky Way would shrink and fade in your sky until it became just another distant spiral among many. You'd be truly alone, drifting through the darkness between islands of stars. These stars are exiles, banished from home by random chance, by being in the wrong place at the wrong time. They'll wander the universe forever, never to return, their fate sealed by a single violent encounter. Even in a galaxy of hundreds of billions of stars, some are cast out, and they continue on, alone, lighting their small corner of the void. The Milky Way's halo contains streams of stars. These stellar streams are like rivers in the sky, long, thin structures of stars tracing out the orbits of disrupted dwarf galaxies. As a small galaxy falls into the Milky Way, Tidal forces stretch it into a long stream that wraps around the larger galaxy like thread around a spool. The streams are faint and difficult to detect because they're spread over such vast areas. But surveys like the Sloan Digital Sky Survey and the Gaia mission have revealed dozens of them, each marking the death of a smaller galaxy. These streams contain information about the Milky Way's gravitational field. As they orbit, they're influenced by all the mass in the galaxy, visible and dark. By studying their shapes and motions, astronomers can map the distribution of dark matter in the halo. In a sense, these streams are ghosts, the remnants of galaxies that no longer exist, now just long trails of stars on elliptical orbits. They'll eventually mix into the general stellar population. Their identity lost, but for now they remain distinct, still tracing the path of their final journey. Everything leaves a trace. Even something destroyed continues to exist in some form, its pattern persisting long after its structure has dissolved. The Milky Way produces a few supernovae per century. These catastrophic stellar explosions are rare but dramatic. A single star briefly outshines billions of others, releasing as much energy in a few weeks as the Sun will produce in its entire lifetime. Then it fades, leaving behind either a neutron star or a black hole. On average, the Milky Way experiences about 1 to 3 supernovae per century, though the exact rate is uncertain because dust blocks our view of much of the galaxy. We can detect supernovae in other galaxies easily, but in our own, they're often hidden. The last supernova visible to the naked eye in the Milky Way was in 1604, Kepler's supernova. Before that was Tycho's supernova in 1572. There may have been others since then that we simply couldn't see because they occurred behind thick dust clouds. Right now, somewhere in the galaxy, a massive star might be in its final moments, its core collapsing, about to explode. The light hasn't reached us yet. We won't know until the flash arrives, decades or centuries from now, depending on the distance. Supernovae are the galaxy's way of recycling matter, of creating heavy elements and scattering them into space. Without them, there would be no iron, no gold, no silver, no planets like Earth. They're destructive but necessary, violent but creative. Even death serves a purpose in the cosmic cycle. Even endings create the possibility of new beginnings. Most stars in the Milky Way are not alone. About half of all Sun-like stars exist in binary or multiple star systems, 2 or more stars orbiting each other. The percentage is even higher for massive stars. Only smaller stars like red dwarfs tend to be solitary. In a binary system, the stars dance around their common center of mass, bound together for billions of years. Some binaries are wide, with the stars separated by hundreds of astronomical units, taking centuries to orbit each other. Others are close, the stars nearly touching, whipping around each other in just hours or days. Living on a planet in a binary system would be strange. You might have 2 suns in the sky, creating complex patterns of day and night. Or if your planet orbits far from the binary pair, you'd see them as a single bright point, brighter than any star in our sky. Some binary systems are even more complex, triple or quadruple star systems, intricate gravitational dances that somehow remain stable over cosmic time. The nearest star system to Earth, Alpha Centauri, is actually a triple system, 2 sun-like stars in close orbit plus Proxima Centauri, a red dwarf orbiting farther out. The galaxy is full of partnerships, companions, stars that have never known solitude. And there's something almost comforting in that. Even stars don't face the universe alone. The Milky Way's rotation is surprisingly uniform. In our solar system, the inner planets orbit faster than the outer ones. This is true of any system dominated by a central mass. The closer you are, the faster you orbit. But galaxies don't work this way. The rotation curve of the Milky Way, a graph of orbital speed versus distance from the center, stays remarkably flat over most of the disk. Stars far from the center orbit at nearly the same speed as stars closer in. This shouldn't be possible if visible matter were all there is. This flat rotation curve is one of the key pieces of evidence for dark matter. The only way to explain it is if the galaxy is embedded in a massive halo of invisible matter that extends far beyond the visible disk. This dark matter's gravity pulls on the outer stars, speeding them up beyond what they should be. It's one of the universe's great mysteries. The thing that holds galaxies together, that makes up most of their mass, is completely unknown to us. We've given it a name, dark matter, but we have no idea what it actually is. The galaxy spins steadily, uniformly, held together by something we can't see. Perhaps that's a metaphor worth contemplating as you drift towards sleep, that invisible forces can hold things together, that not everything needs to be seen to be real. The Milky Way's disk has two distinct populations of stars. The thin disk, where the Sun lives, contains younger, metal-rich stars orbiting in a relatively flat plane. The thick disk, overlapping but extending higher and lower, contains older, metal-poor stars with more random orbits. These two populations tell us about the galaxy's history. The thick disk likely formed first, in a more chaotic era when the young galaxy was still accreting material and experiencing frequent mergers. Its stars were scattered into their tilted orbits by gravitational interactions with other galaxies. The thin disk formed later, after the galaxy had settled down. Gas that wasn't yet incorporated into stars gradually settled into a flat, rotating disk, and new stars formed from this material. These younger stars inherited the disk's ordered rotation. If you look at a star's motion, its composition, and its age, you can often tell which population it belongs to. The thick disk stars are travelers, their orbits taking them high above the galactic plane before plunging back down. Thin disk stars like the Sun stay close to the plane, circling sedately. Even within a single galaxy, there are neighborhoods, districts, populations with different characteristics and histories. The galaxy has layers, structure, a subtle architecture revealed only by careful study. The Sun has orbited the galaxy about 20 times since it formed. Our solar system is 4.6 billion years old. A galactic year, one complete orbit around the galaxy, takes about 225 to 250 million years. Simple division gives you 18 to 20 orbits. Each orbit has carried the solar system through different environments. Sometimes we've been in the dense spiral arms, surrounded by young stars and nebulae. Other times we've been in the quieter interarm regions, as we are now. We've passed close to other stars, though not close enough to disturb the planets. We've moved through clouds of gas and dust. Earth itself has changed dramatically during this time. When the solar system was at this exact position 225 million years ago, dinosaurs had not yet evolved. The supercontinent Pangaea was intact. The Atlantic Ocean didn't exist. Life was simpler, smaller, confined to water and land near water. One galactic year ago, there were no mammals, no birds, no flowers. 2 galactic years ago, complex life was just emerging on land. 20 galactic years ago, Earth was a hellish, molten world, barely cooled enough to have a solid crust. The galaxy is our larger clock, our cosmic calendar. Its rotation marks time on scales almost too vast to comprehend. Yet here we are, passengers on this ancient carousel, spinning through space. The Milky Way contains massive star-forming regions. Places like the Tarantula Nebula in the Large Magellanic Cloud, technically a satellite galaxy, but part of the Milky Way system, are forming stars at prodigious rates. The Tarantula Nebula alone is creating stars with enough mass to equal several thousand suns. Closer to home, regions like the Carina Nebula, about 7,500 light-years away, are similarly active. These nebulae are glowing clouds of gas illuminated by the intense radiation from young, massive stars. The ultraviolet light from these stars ionizes the surrounding gas, making it glow in beautiful reds and blues. These regions are violent and chaotic. The radiation and stellar winds from massive stars push gas around, triggering new waves of star formation even as they disrupt the cloud that gave birth to them. Massive stars live fast and die young, exploding as supernovae that further compress nearby gas, triggering yet more star formation. Through a telescope, these nebulae are among the most spectacular objects in the sky. Vast clouds glowing with their own light, pillars of dust silhouetted against bright backgrounds, clusters of newborn stars embedded in glowing gas. Creation isn't always gentle. Sometimes it's messy, violent, chaotic. But the result is the same: new lights dawning in the darkness, new possibilities emerging from old material. The Milky Way's stars have different metallicities. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. Stars with high metallicity formed from gas enriched by previous generations of stars. Stars with low metallicity formed from more pristine material. The Sun has relatively high metallicity. About 2% of its mass is elements heavier than helium. This tells us it formed from gas that had been cycled through stars before, gas enriched by supernovae and stellar winds. The oldest stars in the galaxy have metallicities less than 1% that of the Sun, some less than 0.1%. They formed from nearly pure hydrogen and helium, the primordial material left over from the Big Bang. By studying these metal-poor stars, astronomers can learn about the conditions in the early universe. There's a general trend. The older the star, the lower its metallicity. But there are exceptions: stars captured from dwarf galaxies, stars formed in unusual environments. Each star's metallicity is like a chemical fingerprint, telling the story of its birth. We are made of high metallicity material, third or fourth generation star stuff. The atoms in your body have been through multiple stars, forged in cores and explosions, ejected into space, incorporated into new clouds, and finally into the solar system and Earth and you. You are recycled material in the most cosmic sense, ancient and new at once. The Milky Way is part of the local group. This is a collection of about 80 galaxies bound together by gravity, spanning about 10 million light-years. The Milky Way and Andromeda are the two largest members, with the Triangulum Galaxy a distant third. Most of the local group's members are small dwarf galaxies, faint, sparse collections of stars orbiting one of the larger galaxies. Some are irregular in shape, disrupted by tidal forces or past collisions. Others are dwarf spheroidals, round and smooth but incredibly dim. The local group is isolated from other galaxy groups by vast regions of nearly empty space. The nearest large galaxy cluster, the Virgo cluster, is about 50 million light-years away. Between here and there, there's mostly darkness. Within the local group, galaxies interact. They orbit each other, exchange material through tidal streams, sometimes collide. It's a small community in cosmic terms, a family of galaxies sharing a common region of space. And someday, the Milky Way and Andromeda will merge, combining the local group's two giants into one enormous elliptical galaxy. But we'll come to that story soon enough. For now, just know that even galaxies don't exist in isolation. They have neighbors, companions, communities. The universe is structured at every scale. There are regions of the Milky Way we cannot see. The galactic plane is thick with dust, especially toward the center. This dust absorbs visible light, creating zones of avoidance where we simply can't see what's beyond. Entire regions of the galaxy are hidden from us, not by distance but by intervening matter. Infrared and radio telescopes can peer through the dust to some extent, revealing what visible light telescopes cannot. But even so, our view is incomplete. There could be stars, nebulae, even entire stellar clusters hidden behind the thickest dust clouds, invisible to all our instruments. The zone of avoidance, the region of sky blocked by the galactic disk, also prevents us from seeing distant galaxies in that direction. Entire clusters of galaxies might lie hidden behind the Milky Way, their existence unknown to us. It's humbling to realize that our own galaxy blocks our view of the universe. We're inside the thing we're trying to study, and that position comes with limitations. No matter how advanced our telescopes become, there will always be parts of the cosmos hidden from us by sheer geography. The universe keeps secrets, not out of malice, but simply by virtue of its structure. And perhaps that's okay. Perhaps not everything needs to be known. The Milky Way's stellar halo extends for hundreds of thousands of light-years. Beyond the visible disk, in the diffuse halo surrounding the galaxy, individual stars and globular clusters orbit on highly elliptical paths. This halo is roughly spherical, extending far into intergalactic space. The stars in the halo are old metal-poor relics from the galaxy's early days, or stars captured from disrupted dwarf galaxies. They're widely spaced, with vast distances between them. If you lived in the halo, your nearest stellar neighbor might be light-years away, and the Milky Way's disk would appear as a beautiful spiral far below you. The halo also contains most of the galaxy's dark matter. This invisible material dominates the halo's mass, though we detect it only through its gravitational effects. The halo's extent is uncertain. It likely fades gradually into intergalactic space without a sharp boundary. Mapping the halo is difficult because its stars are so sparse and dim. But missions like Gaia are gradually revealing its structure, tracing stellar streams and measuring the motions of halo stars with unprecedented precision. The halo is the galaxy's outermost layer, its diffuse boundary with the void beyond. And it's larger than most people imagine. The visible disk is just the bright center of a much larger structure. The Milky Way's gas is being recycled constantly. Gas ejected by dying stars, through stellar winds and supernova explosions, enriches the interstellar medium with heavy elements. This material mixes with existing gas and eventually collapses to form new stars, which in turn live and die and return their material to space. This galactic fountain, as it's sometimes called, is a continuous cycle. Material flows from stars into space, cools and condenses into clouds, forms new stars, and repeats. Over billions of years, the same atoms have likely been through multiple stars. The oxygen you're breathing right now was forged in a star that died before the sun formed. The carbon in your body likewise. These atoms have been recycled through the galaxy's gas cycle multiple times, incorporated into different stars, ejected, recaptured. Nothing in the galaxy is truly new. Everything is recycled, repurposed, used again and again. The galaxy is efficient this way, wasting nothing, transforming death into the raw material for new life. It's a closed loop mostly. Some gas is lost into intergalactic space, blown out by supernovae or stellar winds. And some gas falls into the galaxy from outside, fresh material from the cosmic web. But mostly, the galaxy recycles itself, endlessly creative with its finite supply of matter. The Milky Way has a thick disk of old stars. Overlapping the thin disk where most stars, including the Sun, reside, there's a thicker population of older stars with more random orbits. These stars can venture far above or below the galactic plane, thousands of light years up or down. The thick disk likely formed earlier than the thin disk, during a more chaotic period in the galaxy's history. Its stars are older, metal-poor, and their orbits suggest they were scattered by gravitational interactions, perhaps with dwarf galaxies that fell into the young Milky Way. If you graph stellar density versus height above the galactic plane, you see two exponential distributions. One thin and concentrated, the thin disk, one thicker and more diffuse, the thick disk. They overlap but are distinct populations. These stars have seen more of the galaxy than the Sun has. Their elliptical orbits carry them through the disk, far into the halo, and back down again, completing each cycle in tens to hundreds of millions of years. They're travelers, wanderers, never staying in one neighborhood for long. Even within the disk, there are layers, populations, histories written in the motions and compositions of stars. The galaxy is more complex than it appears. Some stars in the Milky Way are older than the galaxy itself. This sounds paradoxical, but it's true. The oldest stars in the galaxy formed about 13.2 billion years ago, when the Milky Way was just beginning to coalesce from smaller protogalactic fragments. The galaxy as a unified structure didn't fully form until later. These ancient stars are found in globular clusters and the stellar halo. They're survivors from the galaxy's formative era, when conditions were different, more chaotic, less organized. They've witnessed the entire history of the Milky Way, from its birth to its current majestic spiral form. Some of these stars may have formed outside what would become the Milky Way, in smaller systems that were later absorbed. They're older than their current home, immigrants from lost galaxies. It's strange to think about stars existing before the galaxy they now inhabit. But galaxies are built from smaller pieces, assembled over time. The oldest stars remember a time before the Milky Way, though of course they don't remember in any conscious sense. They simply persist, shining steadily, their light a record of ancient times. Time is complicated in the universe. Beginnings are gradual, not sharp, and some things predate the structures they're now part of. The Milky Way's central bulge is ancient. The bulge, the bright, roughly spherical region at the galaxy's center, contains mostly old, red stars. These stars formed in the galaxy's early days, when gas was still falling inward toward the center, colliding and triggering intense bursts of star formation. The bulge is crowded. Stars are packed much more densely there than in the disk. If the Sun were located in the bulge, the night sky would be spectacular, thousands of stars bright enough to cast shadows, the sky never truly dark. But the bulge is also chaotic. Stars there move on complex orbits, influenced by the central supermassive black hole and by each other. There's no ordered rotation like in the disk, just a swarm of stars moving in various directions. The bulge formed quickly, probably within the first billion years of the galaxy's existence. Since then, it has aged quietly, its stars growing redder as the massive ones die off, leaving only the long-lived low-mass stars. Looking at the bulge is like looking at the galaxy's core, its heart, the place where everything began. Ancient, crowded, glowing softly with the light of aged stars. The Milky Way experiences periodic passages through the galactic plane. As the solar system orbits the galaxy, it doesn't stay precisely in the plane of the disk. Instead, it oscillates up and down, passing through the plane roughly every 30 million years. Some scientists have speculated that these passages might have subtle effects on Earth. Perhaps increased exposure to cosmic rays or gravitational perturbations from dense gas clouds could influence climate or even extinction events. The evidence is weak and controversial, but it's an intriguing idea. What's certain is that our environment changes as we orbit. Sometimes we're in dense spiral arms, sometimes in quieter regions. Sometimes we're above the plane, sometimes below. Our local cosmic neighborhood is constantly shifting. Right now, we're slightly above the galactic plane, about 60 light-years above, and moving upward. In about 15 million years, we'll reach our maximum height above the plane, about 230 light-years, then fall back down, cross through the plane, continue downward, and eventually return. It's a gentle bobbing motion, like a horse on a carousel that also moves up and down as it circles. And Earth comes along for the ride, its history possibly influenced by these cosmic rhythms. The Milky Way's spiral arms are sites of intense star formation. When giant molecular clouds enter a spiral arm, they get compressed by the density wave, triggering gravitational collapse and star formation. This is why spiral arms appear bright and blue. They're full of young, massive stars. These massive stars are so short-lived that they never make it out of the spiral arm before dying. They're born in the arm, live briefly, a few million years, and explode as supernovae all within the arm's boundaries. Their blue light defines the spiral structure. Longer-lived stars like the Sun, by contrast, drift in and out of spiral arms during their galactic orbits. The Sun has probably passed through spiral arms multiple times since it formed. Each passage would have lasted a few million years, long enough to be significant, but a small fraction of the Sun's total lifespan. During these passages, the solar system might experience increased rates of comet impacts or cosmic ray exposure as it moves through denser regions. But the effects, if any, are subtle and difficult to detect in the geological record. The spiral arms are the galaxy's nurseries, its factories of creation. And they come and go, forming and dissolving over hundreds of millions of years, leaving only their newest children, the massive stars, to mark their current positions. The Milky Way contains mysterious ultra-faint dwarf galaxies. These are the smallest, dimmest galaxies known, tiny systems containing just a few thousand to a few 100,000 stars. They're so faint that they were only discovered in the 21st century, revealed by careful surveys that picked out their stars against the background of the Milky Way. Despite containing few stars, these ultra-faint dwarfs seem to contain enormous amounts of dark matter. Their stars move too fast for the visible mass alone. They're the most dark matter-dominated objects known, with dark matter outweighing visible matter by factors of hundreds or even thousands. Why these galaxies contain so few stars despite having plenty of dark matter is a mystery. Perhaps most of their gas was stripped away by interactions with the Milky Way. Or perhaps star formation was suppressed by feedback from the first supernovae, which could have blown away the remaining gas before more stars formed. These tiny galaxies are fossil remnants from the early universe, small systems that survived while most of their siblings merged into larger structures. Studying them gives us a glimpse into the building blocks from which galaxies like the Milky Way formed. Even the smallest, dimmest things can contain mysteries. Even the faintest whispers can carry important messages if you learn how to listen. The Milky Way's dark matter halo may contain primordial black holes. Some theories suggest that part of the galaxy's dark matter might consist of black holes formed in the early universe, shortly after the Big Bang. These primordial black holes would be small, perhaps just a few times the mass of the Sun, and scattered throughout the halo. If they exist, primordial black holes would be nearly impossible to detect directly. They don't emit light, and they're too small to have significant gravitational effects on visible objects. But they might reveal themselves through rare events like gravitational lensing or collisions with neutron stars. This is speculative, of course. Most physicists think dark matter is a new type of particle, not primordial black holes. But the truth is, we don't know. Dark matter remains one of the biggest unsolved mysteries in physics. The galaxy might be full of invisible black holes, relics from the universe's first moments, drifting silently through space. Or it might not. We're still groping in the dark, trying to understand what most of the universe is made of. There's something humbling about this. We live in a galaxy where most of the mass is unknown to us. We're surrounded by mystery, by things we can detect but not understand. The Milky Way's gas disk is flared at the edges. If you could view the galaxy edge-on, you'd notice that the gas disk, unlike the stellar disk, flares outward at large radii, becoming thicker and puffier toward the edges. This flaring is common in spiral galaxies and is thought to result from the decreasing influence of the stellar disk's gravity at large distances. Without the weight of many stars to compress it, the outer gas can puff up, settling into a thicker disk. The flaring is more pronounced in atomic hydrogen gas than in molecular gas, which is more centrally concentrated. This flared gas disk extends beyond the visible stellar disk, reaching out into regions where few stars shine. It's the galaxy's outermost visible layer, a thin veil of gas marking the transition to intergalactic space. Radio telescopes can map this gas by detecting the 21-centimeter emission line of atomic hydrogen. The maps reveal a disk that's not perfectly flat or circular but lumpy, warped and asymmetric, shaped by interactions with satellite galaxies and the inflow of fresh gas from the cosmic web. Even something as seemingly simple as a gas disk has structure and complexity. Nothing in the universe is perfectly smooth or simple. Everything has texture, detail, irregularities. The Milky Way center is a mysterious place. Besides the supermassive black hole, the galactic center contains a dense stellar cluster, intense magnetic fields, and high-energy phenomena that we don't fully understand. X-ray telescopes reveal bright flares from Sagittarius A*, brief bursts of emission when gas falls toward the black hole. There's also a region called the Central Molecular Zone, a ring of dense gas clouds about 600 light-years across surrounding the center. These clouds are warm, 50 to 100 Kelvin, much warmer than typical molecular clouds, and turbulent, stirred by the motions of massive stars and supernova explosions. Star formation happens here, but it's suppressed compared to what you'd expect given the density of gas. Something about the extreme environment, the strong magnetic fields, the tidal forces from the black hole, the intense radiation, makes it difficult for gas to collapse and form stars. The center is also home to strange features like the Fermi bubbles, the radio arc, a mysterious radio bright filament, and other structures we're still trying to explain. It's a frontier, a place where the galaxy's most extreme physics happens. We can never visit the galactic center, it's too far, and the radiation environment would be lethal. But we can observe it, map it, try to understand it. And in doing so, we learn about the heart of home. Most of the Milky Way's mass is not in stars. Stars, despite their prominence, contribute only about 5 to 10% of the galaxy's total mass. The rest is split between dark matter, about 85 to 90%, and gas, about 5 to 10%. Dark matter dominates. This is true of most galaxies. Stars are the bright, visible component, but they're not where most of the mass resides. The universe is made mostly of things we can't see: dark matter and, on larger scales, dark energy. It's as if stars are just the foam on a vast, dark ocean. They're what we notice, what catches our attention, but they're not the substance. The real mass, the real gravitational anchor, is invisible. This realization fundamentally changed astronomy. We thought we were studying the universe, but we were only studying the visible fraction, a small minority of what's actually there. Most of reality was hidden from us, and it still is. We've given the invisible stuff names: dark matter, dark energy, but we don't know what they are. The universe is mostly mystery, and we're living in the small, bright part that we can see. The Milky Way's rotation period varies with distance from the center. Near the center, stars orbit quickly, completing an orbit in just a few million years. Farther out, orbits take longer. At the Sun's distance, it's 225 to 250 million years per orbit. Even farther out, orbits take longer still, though the orbital velocity paradoxically doesn't decrease much. Hence the flat rotation curve and dark matter mystery. This differential rotation means that the galaxy shears. Stars at different distances slide past each other, like lanes of traffic moving at different speeds. Over time, this shearing should wind up the spiral arms, wrapping them tighter and tighter. But the spiral arms don't get progressively tighter. They persist in their current configuration, which suggests they're not material structures but density waves, patterns that remain even as individual stars move through them. It's a strange thought that the spiral arms aren't actually made of the same stars over time. Stars enter an arm, spend a few million years there, and then drift out again. The pattern persists even as its constituents change. Like a wave on the ocean, the form continues while the substance moves through it. The galaxy's structure is dynamic, flowing, always in motion even when it appears static. The Milky Way is surrounded by a hot corona of gas. Beyond the visible disk and halo, there's a vast, diffuse corona of hot gas, perhaps 1,000,000 degrees Kelvin, extending hundreds of thousands of light years into space. This gas is so hot and thin that it's nearly invisible, detected only through its effects on background light and through faint X-ray emissions. The corona may contain as much mass as all the stars in the galaxy, though it's spread over such a vast volume that its density is incredibly low. If you were somehow immersed in it, you'd barely notice, just a few atoms per cubic centimeter. This hot gas is likely maintained by supernova explosions and stellar winds, which heat gas and blow it outward from the disk. Some of this gas may eventually cool and fall back onto the disk, completing a cycle that takes hundreds of millions of years. The corona is the galaxy's atmosphere, in a sense. Just as Earth has an atmosphere that fades gradually into space, the galaxy has a tenuous envelope of hot gas surrounding its more visible structures. We're embedded in layers: the solar system within the galaxy's disk within the halo within the corona within the local group, and so on. Nested structures, each containing and held by the next. The Milky Way's future is collision with Andromeda. In about 4.5 billion years, the Milky Way and Andromeda galaxies will collide. They're currently approaching each other at about 250,000 miles per hour, drawn together by gravity. The collision is inevitable. But don't worry, this won't be a violent crash. Galaxies are mostly empty space. Stars will pass by each other like ghosts, rarely colliding. What will happen is that the two spiral structures will be disrupted, their ordered rotation replaced by chaos as stars get flung onto new orbits. The process will take billions of years. The galaxies will pass through each other, separate, fall back together, merge again, gradually settling into a single elliptical galaxy. A vast, round system with no disk, no spiral arms, just a smooth distribution of stars. Some have called this merged galaxy Milkometa or Milkdrometa. By the time it forms, the Sun will be nearing the end of its life, swelling into a red giant. Earth, if it still exists, will be uninhabitable, its oceans long since boiled away. So the collision won't affect us or even our distant descendants. But it's a reminder that nothing is permanent. Even galaxies change, merge, transform. The Milky Way, as we know, it has a finite lifespan. The Milky Way contains vast voids between spiral arms. The interarm regions are quieter, less dense, darker. Star formation is reduced here because there's less gas to collapse. The stars that do exist are older, redder, leftover from previous generations. The Sun currently resides in one of these interarm regions, the Orion Spur, a minor arm or perhaps just a bridge between two major arms. It's a peaceful neighborhood, galactically speaking. Not too crowded, not too isolated. In an interarm region, the gas density is lower, the radiation environment gentler. Perhaps this is part of why Earth has been able to develop complex life. We're in a quiet corner of the galaxy, far from the violent star-forming regions and supernova-prone clusters. Or perhaps that's just anthropic reasoning. We exist here, so it must be special. But still, there's something to be said for living in the suburbs rather than downtown. A little distance from the action can be healthy. The spiral arms are the bright, active parts of the galaxy. The interarm regions are the quiet spaces, the darkness between lights. And both are necessary. Both are home to countless stars, each with its own story. The Milky Way's disk is thin compared to its diameter. The ratio of thickness to diameter is about 1 to 100 for the thin disk, like a CD or a vinyl record. This extreme flatness is a result of rotation and angular momentum. As the galaxy formed, gas with net rotation flattened into a disk, with vertical motions dampened by collisions. Stars, once formed, can maintain thicker orbits because they don't collide. But new stars form from gas, which has settled into the thin disk, so new stellar populations are also thin. The thick disk and halo are puffier because their stars formed earlier, when the galaxy was less organized, or because they were scattered into tilted orbits by gravitational interactions. This thinness means that most of the galaxy's volume is actually above or below the disk in the halo. The bright, busy part of the galaxy, where most stars live, is concentrated in a remarkably thin layer. If you could shrink the galaxy down to the size of a swimming pool, the thin disk would be thinner than a sheet of paper floating on its surface. All those hundreds of billions of stars, compressed into an incredibly flat structure. There's something elegant about this flatness. Order emerging from chaos, rotation creating structure, gravity and angular momentum sculpting matter into graceful, efficient forms. The Milky Way's magnetic field may help confine cosmic rays. Cosmic rays are high-energy particles, mostly protons, that zip through space at nearly the speed of light. They come from supernova explosions, pulsars, and other violent events. The galaxy's magnetic field helps trap these particles, preventing them from escaping immediately into intergalactic space. Instead, cosmic rays bounce around within the galaxy, spiraling along magnetic field lines, gradually diffusing outward. This confinement means that cosmic ray densities in the galaxy are higher than they would be otherwise, which has implications for everything from star formation to the evolution of life. Too many cosmic rays can be harmful. They cause mutations, break apart molecules, make space hazardous. But the galaxy's magnetic field provides some shielding, keeping cosmic ray levels from getting too extreme. It's another example of invisible architecture, magnetic fields we can't see, protecting and shaping the galaxy's interior environment. Everything is connected through subtle forces. Even now, cosmic rays are passing through you, through your body, through the Earth. Most pass harmlessly, leaving no trace. A few interact with atoms in your cells, causing tiny, usually insignificant changes. You're being gently irradiated by the galaxy's high-energy particles right now, as you lie here. But don't worry, life has evolved in this environment. We're adapted to it. It's part of what it means to live in a galaxy. The Milky Way has experienced major mergers in its past. About 10 billion years ago, the young Milky Way collided with a dwarf galaxy nicknamed Gaia Enceladus, after the Gaia spacecraft that helped discover evidence of it. This collision sent shockwaves through the galaxy, scattering stars into the thick disk and halo. We can still detect the remnants of Gaia Enceladus, stars with unusual orbits and chemical compositions, moving through the galaxy in coherent streams. These stars remember their origin, even though their parent galaxy was destroyed billions of years ago. There were likely other mergers, too. The Milky Way has been built up over time from smaller galaxies, each collision adding new stars and reshaping the structure. The galaxy's history is written in the motions and compositions of its stars, if you know how to read it. These ancient collisions were transformative events, reshaping the galaxy's structure, triggering bursts of star formation, stirring up the disk. But they happened so long ago that most traces have faded. Only subtle clues remain. Odd stellar orbits, unusual chemical abundances, streams of stars that don't quite fit the pattern. The galaxy has been through trauma and emerged transformed. Its current beautiful spiral form is the result of a violent, chaotic past. Order from disorder, beauty from violence. The Milky Way's globular clusters are among the oldest objects in the universe. Some globular clusters are 12 to 13 billion years old, nearly as old as the universe itself. They formed in the early days when the galaxy was still coalescing, and they've survived essentially unchanged ever since. Inside a globular cluster, stellar densities can be millions of times higher than in the solar neighborhood. Stars are packed so closely that close encounters and even collisions are relatively common. This creates exotic objects, blue stragglers, stars that look younger than they should be, rejuvenated by collisions or mass transfer, millisecond pulsars, X-ray binaries. Globular clusters orbit the galaxy's center in elliptical paths, spending most of their time in the halo. They're like a swarm of bees around the galaxy, each cluster a tight ball of ancient stars following its own orbital path. Looking at a globular cluster through a telescope is like looking back in time. These stars are fossils, relics from the early universe, barely changed since they formed. They've witnessed almost the entire history of the cosmos, and they'll continue for trillions of years more, outlasting most other structures in the universe. The globular clusters are the galaxy's elders, its memory, its connection to the distant past. The Milky Way is losing gas to intergalactic space. Supernova explosions and stellar winds create hot bubbles of gas that expand outward, sometimes breaking through the disk and escaping into the halo or even into intergalactic space. This galactic fountain, or galactic wind, carries material out of the galaxy. Some of this gas eventually cools and falls back onto the disk, completing a cycle. But some escapes entirely, lost to intergalactic space. Over billions of years, the galaxy is slowly losing mass this way. At the same time, The galaxy is accreting fresh gas from the cosmic web, filaments of gas that thread through intergalactic space, connecting galaxies. This infall of fresh, metal-poor gas provides raw material for new star formation. The balance between outflow and inflow determines how long the galaxy can continue forming stars. If more gas is lost than gained, star formation will eventually slow and stop. If inflow exceeds outflow, star formation continues. Currently, the Milky Way seems to be in rough balance, losing and gaining gas at similar rates. But this balance may shift over time, especially after the collision with Andromeda, which will disrupt gas flows and trigger intense bursts of star formation. The galaxy breathes, in a sense, inhaling gas from the cosmic web, exhaling hot gas into the halo. A slow, patient respiration spanning hundreds of millions of years. The Milky Way contains mysterious high-velocity clouds. These are clouds of neutral hydrogen gas moving at high speeds relative to the disk, hundreds of kilometers per second. They're scattered throughout the halo, some falling toward the disk, others moving away. The origin of high-velocity clouds is debated. Some may be gas from the galactic fountain, blown out of the disk and now falling back. Others may be remnants of tidally disrupted dwarf galaxies. Still others might be pristine gas from the cosmic web, falling into the galaxy for the first time. When these clouds collide with the disk, they can trigger star formation. The impact compresses gas in the disk, causing it to collapse and form new stars. So high-velocity clouds may be one mechanism for replenishing the galaxy's supply of star-forming gas. They're invisible to the naked eye, detectable only through radio observations of the 21-centimeter hydrogen line. But they're there, scattered through the halo like raindrops falling toward a pond, each one carrying the potential to create new stars. The galaxy's environment is richer and more complex than it appears. There are layers of structure, populations of objects invisible in optical light, processes happening at scales and in wavelengths we can't perceive directly. The Milky Way's stars have different ages. The galaxy contains stars of all ages, from the 13-billion-year-old globular cluster stars to stars born just a few million years ago. This age spread tells us that star formation has been continuous throughout the galaxy's history. You can estimate a star's age from its properties. The most massive stars burn out quickly, lasting only millions of years, so any very massive, bright blue star must be young. Lower mass stars live much longer, so age determination is harder, but techniques exist based on stellar evolution models and chemical compositions. The Sun is about 4.6 billion years old, making it middle-aged by galactic standards. Seen about one-third of the galaxy's history. Many stars are older, many are younger. The Sun is unremarkable in this respect, just another star among hundreds of billions. This continuity of star formation means the galaxy is always renewing itself. Old stars die, new ones are born. The total number of stars stays roughly constant, but the population is always changing, always cycling through generations. It's like a forest where old trees fall and new ones grow. The forest persists even as its individual members change. The galaxy is a living system in its own slow, patient way. The Milky Way's center was more active in the past. Evidence suggests that Sagittarius A*, the supermassive black hole at the galaxy's center, was actively feeding a few million years ago. During this period, it would have been much brighter, shining as an active galactic nucleus, a quasar essentially, though not as luminous as the most extreme examples. The Fermi bubbles, those vast structures of hot gas extending above and below the galactic plane, may be remnants of this active period. Some event, either intense star formation or black hole feeding, released enormous energy that blew gas outward, creating the bubbles. Today, Sagittarius A* is relatively quiet, accreting only small amounts of gas. But occasionally, a gas cloud or even a star wanders too close, and there's a brief flare of activity. These flares are small compared to the galaxy's active past, but they remind us that the central black hole is still there, still capable of violence. If the black hole were feeding actively, the galactic center would be far more dangerous. Intense radiation would sterilize nearby regions, making life impossible for hundreds or thousands of light years around it. We're fortunate to live in a quiet era with a dormant black hole. The galaxy has moods, periods of activity and quiet. Right now, we're in a calm period, but that can change. The Milky Way's disk shows signs of recent perturbations. Detailed studies of stellar positions and motions have revealed that the disk isn't perfectly smooth. There are ripples, waves in the distribution of stars, as if something disturbed the disk recently in galactic terms. One hypothesis is that a dwarf galaxy passed through the disk a few 100 million years ago, causing these ripples. The disk responded like a drum struck by a hammer, oscillating in response to the perturbation. These oscillations are gradually damping out, but they're still detectable. Another possibility is that the ripples are caused by the passage of a massive dark matter clump through the disk. Or they might be related to the bar at the galaxy's center, which can send density waves propagating outward through the disk. Whatever the cause, the disk is not in perfect equilibrium. It's still responding to past events, still settling down from disturbances. The galaxy is a dynamic, evolving system, not a static structure frozen in time. Even on the largest scales, nothing is perfectly still. Everything is in motion, responding to forces, adjusting to disturbances. The universe is restless, always changing, never quite at rest. The Milky Way's rotation is gradually slowing. Very, very slowly, the galaxy's rotation rate is decreasing due to interactions with satellite galaxies and the loss of angular momentum through gravitational interactions. The timescale for this slowing is enormous, many billions of years, but it's happening. Eventually, after the merger with Andromeda, the resulting elliptical galaxy will have much less net rotation than the current Milky Way. Elliptical galaxies are supported more by the random motions of their stars than by ordered rotation. But don't worry about the slowing affecting anything in the foreseeable future. The change is minuscule on human or even geological timescales. It's relevant only over billions of years, as the galaxy evolves and transforms. Everything in the universe is subject to friction, drag, dissipation, even galaxies. Nothing spins forever unchanged. Energy gets redistributed, angular momentum gets transferred, systems evolve toward equilibrium. The galaxy is winding down very slowly, heading toward a state of lower rotation and higher entropy. But that final state is still unimaginably far in the future. The Milky Way contains exotic stellar remnants. Scattered throughout the galaxy are the remnants of dead stars, white dwarfs, neutron stars, and black holes. These objects are difficult to detect because they're small and dim or completely dark, but they're there in large numbers. White dwarfs are the most common, Earth-sized embers of burnt-out stars, slowly cooling over trillions of years. The galaxy likely contains billions of them, the final fate of all stars like the Sun. Neutron stars are rarer, the collapsed cores of massive stars that exploded as supernovae. They're incredibly dense, with the mass of the Sun compressed into a sphere just 20 kilometers across. Some neutron stars are pulsars, spinning rapidly and beaming radiation into space like cosmic lighthouses. And then there are stellar mass black holes, formed when the most massive stars collapse. These are completely invisible except through their gravitational effects. The galaxy likely contains millions of them, dark and silent, drifting through space. These remnants are the galaxy's graveyard, its collection of ended stories. Each one was once a shining star, and now it's something else. A dense, strange object, a footnote to a stellar life. But even in death, these objects play roles. White dwarfs can explode as supernovae if they accrete enough mass from a companion star. Neutron stars and black holes can merge, releasing gravitational waves. Nothing is truly inert. The Milky Way's spiral pattern may be caused by density waves. The leading theory for spiral arm formation is that they're density waves, regions where stars and gas are temporarily compressed as they move through the pattern. The pattern itself rotates at a different speed than the stars, creating the spiral structure. Think of it like a traffic jam on a highway. Cars enter the jam, slow down, bunch up, and then exit the jam and speed up again. The jam itself moves more slowly than the cars. Similarly, stars enter a spiral arm, spend some time there, and then exit while the spiral pattern persists. This density wave theory explains why spiral arms contain young stars. The compression triggers star formation. It also explains why spiral arms don't wind up tighter over time, which would happen if they were material structures rotating with the disk. But the exact mechanism that creates and maintains the density waves is still debated. It may involve interactions with the central bar, gravitational resonances, or perturbations from satellite galaxies. The galaxy's spiral structure remains partially mysterious. Even the most prominent features of the galaxy, its beautiful spiral arms, are not fully understood. We've made progress, but questions remain. And perhaps that's okay. Perhaps some mysteries are meant to persist, to remind us of how much we still have to learn. The Milky Way's gas is mostly hydrogen. About 90% of the gas in the interstellar medium is hydrogen, with most of the rest being helium. Heavier elements make up only about 1 to 2% of the gas by mass, what astronomers call metals, though chemists would disagree with that terminology. This composition reflects the origin of matter in the universe. The Big Bang produced mostly hydrogen and helium. Everything heavier was created later inside stars through nuclear fusion. Each generation of stars enriches the interstellar medium with slightly more heavy elements. The Sun and its planets formed from gas that had been enriched by previous generations of stars. That's why Earth has iron, silicon, oxygen, elements that didn't exist in the early universe. We're made of second or third or fourth generation material. But even now, after billions of years of stellar processing, the galaxy's gas is still mostly hydrogen. The universe hasn't had time to convert much of it into heavier elements. We're still living in a hydrogen-dominated cosmos. There's something primordial about hydrogen, the simplest atom, one proton and one electron. It's the universe's default element, the raw material from which everything else is built. The Milky Way's stellar disk is slightly lopsided. Detailed measurements show that the disk isn't perfectly symmetric. One side has slightly more stars or gas than the other, creating a subtle lopsidedness. This asymmetry is common in spiral galaxies and may result from interactions with satellite galaxies or recent mergers. The lopsidedness is small, only a few % difference from one side to the other. You wouldn't notice it visually, but precise measurements of stellar densities and gas distributions reveal the asymmetry. This imperfection is a reminder that galaxies are shaped by their histories. Every interaction, every merger, every gravitational tug leaves traces. The galaxy's current form is the sum of everything that's happened to it, and nothing that happens is perfectly symmetric. We like to imagine galaxies as perfect spirals, beautifully symmetric, but reality is messy. There are lumps, asymmetries, irregularities. And maybe that's part of what makes them interesting. Their imperfections tell stories. The Milky Way produces neutrinos constantly. These ghostly particles are produced by nuclear reactions in stars, by supernova explosions, and by cosmic ray interactions in the interstellar medium. Trillions of neutrinos from the sun alone pass through your body every second. Neutrinos barely interact with matter. They pass through planets, stars, even entire galaxies without noticing. Only very rarely does a neutrino collide with an atom. This makes them incredibly difficult to detect, but also incredibly informative when we do detect them. The galaxy is flooded with neutrinos, an invisible sea of particles carrying information about stellar interiors and violent events. They're everywhere, passing through everything, connecting all parts of the galaxy in an instant, since they travel at nearly the speed of light. Right now, neutrinos from the galactic center are passing through you. Neutrinos from distant supernova explosions that happened centuries ago. Their light just now arriving at Earth. Neutrinos from the sun, created in its core 8 minutes ago. You're immersed in this invisible flux, this cosmic neutrino background. It's one more way you're connected to the galaxy, even if you can't feel it. The Milky Way's oldest stars have almost no heavy elements. The most metal-poor stars in the galaxy have iron abundances less than 1/millionth that of the Sun. They formed from gas that had been enriched by only 1 or 2 previous supernovae, gas that was still nearly primordial. These ultra-metal-poor stars are rare and precious to astronomers because they provide a window into the very early universe. By studying their compositions, we can learn about the first stars, the ones that created the first heavy elements, even though those first stars are long gone. Some ultrametal-poor stars show unusual abundance patterns, with some heavy elements enhanced and others depleted. These patterns tell us about the specific supernovae that enriched their birth clouds, whether they were normal core collapse supernovae or rare, peculiar events. These ancient stars are like time capsules, preserving information about conditions in the early galaxy. They're survivors from a different era, when the universe was younger, simpler, stranger, and they're still shining patiently, outlasting almost everything. In a sense, they're the galaxy's memory, carrying chemical records of ancient times in their atmospheres. The Milky Way's mass is difficult to measure precisely. Estimates for the galaxy's total mass range from about 700 billion to 2 trillion times the mass of the Sun, depending on how far out you include the dark matter halo. The uncertainty comes from the difficulty of measuring the extent and density of dark matter. Most methods rely on measuring the motions of satellite galaxies or stellar streams and using their orbits to infer the galaxy's mass. But these measurements are tricky and model-dependent, leading to a wide range of estimates. Recent measurements using Gaia data have refined the estimates, but significant uncertainty remains. We don't know the mass of our own galaxy to better than a factor of 2. It's humbling. We can measure the masses of distant galaxies more easily than our own, because we can see them from the outside. Being inside the Milky Way makes some things easier. We can see individual stars, study them in detail. But it makes other things harder. We can't see the big picture, can't step back and view the whole structure at once. Perspective matters. Sometimes being close makes it harder to see clearly. The Milky Way's stars have different metallicities. Stars born at different times and in different locations have different chemical compositions. This chemical evolution, reflects the gradual enrichment of the interstellar medium with heavy elements over time. The oldest stars are metal-poor, born from nearly pristine gas. Younger stars like the Sun are metal-rich, formed from gas enriched by many previous generations of stars. And stellar metallicity varies with location. Stars near the galactic center tend to be more metal-rich than stars in the outer disk or halo. By measuring a star's metallicity, astronomers can estimate its age and place of origin. Metallicity is like a chemical fingerprint, telling the star's story. Stars captured from dwarf galaxies often have unusual metallicity patterns, marking them as outsiders. The galaxy stars are a chemical library, recording the history of element production and mixing. Each star is a data point in the story of the galaxy's enrichment, a marker of when and where it formed. We can read this story, slowly piecing together the galaxy's history one stellar spectrum at a time. The Milky Way is part of a larger supercluster. Beyond the local group lies the Virgo supercluster, a vast collection of galaxy groups and clusters spanning about 110 million light-years. The Milky Way, Andromeda, and the rest of the local group are part of this larger structure. But recent mapping has revealed an even larger structure called Laniakea, a supercluster of superclusters, containing about 100,000 galaxies and spanning 520 million light-years. The name means immeasurable heaven in Hawaiian, fitting for something so vast. Laniakea is defined by the flow of galaxies toward its center of mass, called the Great Attractor. Everything in Laniakea, including the Milky Way, is slowly falling toward this gravitational center, though the motion is subtle compared to local motions within the local group. These structures, groups, clusters, superclusters, form the cosmic web, the large-scale structure of the universe. Galaxies are not randomly scattered but organized into filaments and sheets, with vast voids in between. The Milky Way is a tiny part of this cosmic tapestry, one thread in an incomprehensibly vast weave. And that tapestry extends as far as we can see, perhaps infinitely far beyond that. The Milky Way's bulge rotates like a bar. The central bulge isn't spherical but somewhat boxy, and it rotates as a rigid body, more like a solid bar than a fluid sphere. This bar structure is thought to have formed from instabilities in the disk, perhaps several billion years ago. The bar influences the motions of stars and gas throughout the inner galaxy. As material moves near the bar, it gets flung onto specific orbits, creating patterns of inflow and outflow. The bar can drive gas toward the center, feeding star formation and perhaps feeding the central black hole. Bars are common in spiral galaxies, about 2/3 have them. They seem to be a natural outcome of disk evolution, forming when certain resonances and instabilities develop. Once formed, bars are generally stable, persisting for billions of years. Living in a barred spiral has interesting consequences. The bar creates gravitational resonances at specific distances, affecting stellar orbits. The Sun is far enough from the bar that its orbit is mostly unaffected, but stars closer in feel the bar's influence strongly. The galaxy's heart is not spherical and symmetric but elongated, rotating, dynamically active. Even the core has structure, organization, movement. The Milky Way contains dust lanes. If you look at images of the Milky Way taken at visible wavelengths, you see dark lanes cutting through the bright band of stars. These are dust lanes, regions where microscopic grains of dust block the light from stars beyond. Dust is created by stars, especially cool giant stars and supernovae, which eject material into space. This material includes tiny solid grains, silicates, carbon, iron, that form in the cooling gas. These grains are incredibly small, about the size of smoke particles. Despite their small size, dust grains have a big effect. They absorb and scatter light, preferentially blocking shorter, bluer wavelengths and letting longer, redder wavelengths pass. This makes objects behind dust appear redder than they should, an effect called interstellar reddening. Dust also emits its own light in the infrared, warmed by starlight and glowing thermally. Infrared telescopes like Spitzer and Herschel have mapped this dust emission, revealing the distribution of dust throughout the galaxy. Dust is annoying to optical astronomers because it blocks their view. But it's also important. Dust provides the seeds for planet formation, and without it, rocky planets like Earth couldn't form. The Milky Way's spiral arms may come and go. Computer simulations suggest that spiral arms are transient features, forming and dissolving over hundreds of millions of years. The current spiral structure of the Milky Way may not have existed a billion years ago and may not exist a billion years from now. This transience is related to the density wave nature of spiral arms. The patterns shift and change as the disk's gravitational field evolves, as satellite galaxies pass by, as gas is consumed and replenished. The galaxy's appearance changes over time, though slowly by human standards. This means that the beautiful spiral structure we see today is temporary, a current configuration in an ever-changing system. If we could watch the galaxy in time-lapse over billions of years, we'd see the spiral pattern shift, arms appearing and disappearing, the structure flowing like a slow-motion fluid. Nothing is permanent, not even the galaxy's grand spiral form. Everything changes given enough time. The universe is dynamic at every scale. The Milky Way is emitting gravitational waves. Every accelerating mass produces gravitational waves, ripples in space-time itself. Binary systems, where two massive objects orbit each other, are particularly strong sources. The galaxy contains many such systems: binary stars, black holes, neutron stars, each producing weak gravitational waves. Individually, these sources are too weak to detect, but collectively, they create a background of gravitational radiation, a faint hum pervading space. Future gravitational wave detectors may be able to detect this galactic background. The strongest sources are close binary systems of compact objects, two white dwarfs or two neutron stars, or a neutron star and a black hole spiraling toward each other. As they orbit, they lose energy to gravitational radiation and slowly spiral inward, eventually merging in a burst of gravitational waves. Several such mergers likely happen in the Milky Way every few million years. If one occurred close enough, within a few thousand light-years, the gravitational waves would be easily detectable by current instruments like LIGO. The galaxy is ringing gently with gravitational waves, space-time itself vibrating with the motions of massive objects. It's yet another invisible layer of reality, a phenomenon we've only recently learned to detect. The Milky Way's disk is still settling. Despite being billions of years old, the galactic disk hasn't reached perfect equilibrium. Stars are still migrating radially as they interact gravitationally with spiral arms and with each other. The disk is slowly evolving, redistributing mass and angular momentum. The Sun, for instance, probably formed closer to the galactic center than it is now. Over its 4.6 billion-year lifetime, it has likely migrated outward by several thousand light-years, pushed by gravitational interactions with spiral density waves. This radial migration means that the galaxy is mixing itself over time. Stars born in the inner disk can end up in the outer disk, and vice versa. The galaxy isn't a static structure with fixed populations but a dynamic, evolving system where everything slowly moves and changes. Even stars that seem settled and stable are actually on long, slow journeys, their orbits gradually changing over billions of years. Nothing stays put. Everything drifts. The galaxy is still finding its final form, still adjusting, still settling into equilibrium, though it may never fully reach it. The Milky Way will eventually run out of star-forming gas. Star formation consumes gas, converting it into stars. While some gas is recycled when stars die, not all of it returns to the interstellar medium. White dwarfs lock up some mass permanently, and some gas escapes into intergalactic space. At current rates, the Milky Way has enough gas to continue forming stars for several more billion years. But eventually, the supply will dwindle. Fewer and fewer new stars will form, and the galaxy will slowly age, its stellar population becoming increasingly dominated by old, red stars. After the merger with Andromeda, there will be a burst of star formation as gas clouds collide. But once that burst subsides and the gas is exhausted, the merged galaxy will slowly fade, becoming a red and dead elliptical galaxy, full of old stars but forming no new ones. This won't happen for many billions of years, but it's the eventual fate of most galaxies, to consume their gas and stop forming stars. The universe is aging, and galaxies age with it. But for now, the Milky Way is still vibrant, still creating new stars, still renewing itself. The sunset is distant. For now, it's still afternoon. Let your breath deepen now. Feel the weight of your body against the bed. Notice how still you are, how quiet, and yet you're moving, orbiting with the Earth around the sun, orbiting with the sun around the galaxy, falling with the galaxy toward distant attractors. All this motion, and yet perfect stillness in your immediate experience. Both are true. You are still and you are moving at tremendous speeds. The universe holds contradictions gently, allowing both to exist at once. The Milky Way continues its ancient rotation, indifferent to your presence yet carrying you along with it. You are part of something vast, something that has existed for nearly the entire history of the universe and will continue long after you're gone. There's comfort in that thought. Your worries are small against this backdrop. Your concerns are real, but they're also temporary, brief flickerings in cosmic time. The galaxy doesn't judge them, simply turns patient and eternal. The Milky Way contains organic molecules. Giant molecular clouds aren't just hydrogen and helium. They also contain complex organic molecules, amino acids, sugars, alcohols, and other carbon-based compounds. The building blocks of life exist out there in space, floating in the dark between stars. These molecules form through chemical reactions on the surfaces of dust grains, shielded from harsh radiation deep inside molecular clouds. When stars form from these clouds, the organic molecules can end up in protoplanetary disks, eventually incorporating into comets and asteroids. Some of these organics may have been delivered to early Earth by comet impacts, seeding our planet with the raw materials for life. Life's ingredients came from space, from the galaxy's molecular clouds, from the patient chemistry that happens in the cold and dark. In a sense, life is a natural product of galactic chemistry. Given enough time, given the right conditions, the molecules that exist in space can assemble into living systems. We're not separate from the galaxy, we're made of it, built from its materials, following its chemical rules. The boundary between living and non-living, between Earth and space, is blurrier than it seems. We're all part of the same cosmic system. The Milky Way's history is written in its stars. Each star is a time capsule, preserving information about the conditions when and where it formed. By studying stellar populations, their ages, metallicities, orbits. Astronomers can piece together the galaxy's history. The thick disk stars tell us about the galaxy's chaotic youth. The globular clusters record the earliest star formation. The thin disk reveals more recent, quieter times. Stellar streams mark absorbed dwarf galaxies, ghosts of smaller systems consumed long ago. It's detective work, looking at clues left behind, inferring what must have happened. The galaxy doesn't keep records consciously, but its structure and content are a record nonetheless, waiting to be read. We're learning to read this record, slowly. Each new survey, each improved measurement, reveals more details of the galaxy's story. We're getting closer to understanding where we came from, how this magnificent structure formed and evolved. But the story is incomplete. Gaps remain, mysteries persist, and perhaps they always will. The past is difficult to reconstruct perfectly, even when clues remain. The Milky Way contains hundreds of billions of worlds. If most stars have planets, and evidence suggests they do, then the galaxy contains hundreds of billions of planets. Rocky worlds, gas giants, ice balls, worlds of types we haven't imagined. Some of these worlds orbit in their stars' habitable zones, regions where liquid water could exist on a planet's surface. There could be billions of potentially habitable worlds in the Milky Way alone, and perhaps some of them harbor life. We don't know yet. We've barely begun to search, but the galaxy seems fertile, full of worlds, full of possibilities. Life may be common or rare, simple or complex, similar to Earth's life or completely alien. Somewhere out there, scattered among the stars, there may be other beings wondering about the galaxy, looking up at their own night sky, asking the same questions we ask. Or maybe not. Maybe we're alone. Both possibilities are profound. The galaxy is full of mystery, full of unknowns. And those unknowns include the biggest questions we can ask. Are we alone? Is life common? Are there others like us, wondering, seeking, exploring? We don't know. Not yet. But someday we might. The Milky Way contains stellar fossils from its earliest days. Certain stars, metal poor, with unusual abundance patterns, are relics from the first few 100 million years of the galaxy's existence. They formed from gas enriched by only one or two supernovae, gas that was still nearly primordial. These stars are precious to astronomers because they contain chemical fingerprints of the very first stars, the ones massive enough to die quickly, creating heavy elements for the first time. By studying these fossil stars, we can infer properties of the first stellar generation, even though those first stars are long gone. It's like archaeology, reconstructing history from fragments and traces. The galaxy remembers its past, encoded in the compositions of its oldest stars. The memory isn't conscious, but it's real, chemical records preserved for billions of years, waiting to be read. Everything has a history. Everything carries traces of its past. And sometimes, if you know how to look, you can read that history, can see back to the very beginning. We've journeyed through the Milky Way tonight, exploring its vast spiral structure, its hundreds of billions of stars, its dark matter halo extending far into intergalactic space. We've touched on mysteries that perplex astronomers and wonders that inspire awe. We've learned that the galaxy is ancient, 13.6 billion years old, nearly as old as the universe itself. That it's been built up over time through the slow accumulation of smaller galaxies, each merger leaving traces in the motions and compositions of stars. We've seen that the galaxy is dynamic, not static. Stars are born from collapsing gas clouds, live for millions or billions of years, and die in various ways, returning their material to space. The galaxy breathes, in a sense, cycling matter endlessly through different forms. We've discovered that the galaxy is mostly invisible. Dark matter makes up 85 to 90% of its mass, holding everything together through gravity alone. We can't see it, can't touch it, can only infer its presence from its effects. We've explored the galactic center, where a supermassive black hole weighing 4,000,000 times the sun sits dormant, occasionally flaring when gas falls too close. We've traced the spiral arms, where young massive stars illuminate clouds of gas and dust. We've learned about the galaxy's satellites, small dwarf galaxies orbiting the Milky Way, slowly being torn apart by tidal forces, their stars scattered into long streams that wrap around the larger galaxy. We've contemplated the galaxy's future, its inevitable collision with Andromeda in 4.5 billion years, the transformation from spiral to elliptical, the slow decline as star formation eventually ceases. And most importantly, we've recognized our connection to all of this. We are made of stellar material, assembled from atoms created in stellar cores and scattered by supernovae. We are the galaxy's way of knowing itself, temporary patterns in its endless cycling of matter. There's something profound in this realization that you are not separate from the cosmos but part of it. Every atom in your body has a history spanning billions of years, cycling through stars, through space, through planetary systems, before finally becoming you. You are ancient and new simultaneously. Your atoms are billions of years old, but their current arrangement, you, is recent, temporary, unique. You've never existed before and will never exist again in quite this form. This perspective can be humbling or liberating or both. Your worries, your anxieties, your daily concerns, they're real and valid, but they're also temporary and small compared to the vast scales of space and time we've explored tonight. The galaxy has existed for 13.6 billion years. It will continue for trillions more. Your life, by comparison, is a brief flicker, decades in a story of eons. And yet your brief flicker matters. You are conscious. You are aware. You can wonder, question, seek to understand. The universe, as far as we know, is mostly unconscious. Stars burning mindlessly, gas flowing according to physical laws, galaxies rotating through empty space. But here and there, perhaps scattered rarely throughout the cosmos, consciousness emerges. Matter becomes aware of itself. You are one such emergence, a way the universe has organized itself locally to create awareness, thought, feeling. Through you, the Milky Way looks back at itself and marvels at its own existence. This is precious. Not because you're the center of anything, you're on an ordinary planet orbiting an ordinary star in an ordinary galaxy among billions. But because consciousness is rare, or at least seems to be, awareness is special. Your existence is improbable when you think about it. The specific atoms that became you could have been anywhere, in any configuration. The molecular cloud that formed the sun could have collapsed slightly differently, and Earth might never have formed. Life could have evolved along different paths, and you specifically might never have come to be. But here you are, against all odds, a temporary arrangement of stellar debris that can think, feel, wonder, and rest. A brief pattern that will dissolve eventually, your atoms returning to the cycle. This isn't sad. It's beautiful. You're part of something vast and ongoing. Your brief existence is a note in a cosmic symphony that has been playing for billions of years and will continue for billions more. And for now, for this brief moment, you exist. You are here, breathing, resting, drifting toward sleep on a small world orbiting a medium-sized star in one of the spiral arms of the Milky Way Galaxy. That's enough. That's more than enough. That's everything. Let yourself sink deeper now, deeper into rest, deeper into the approaching darkness of sleep. Your body knows what to do. Trust it completely. Feel the weight of your head against the pillow, the softness of the bedding beneath you. Notice how still you've become, how quiet. This is good. This is exactly right. Your breathing is so slow now, so gentle. Each breath barely perceptible, each one carrying you closer to sleep. There's no effort involved, no trying. Just allowing, accepting, surrendering. The thoughts that were circling earlier, they've mostly faded now, haven't they? Just wisps remaining, and even those are drifting away like morning mist in sunlight. Soon there will be nothing but the soft darkness of sleep. Imagine yourself floating in space, looking back at the Milky Way. See its beautiful spiral form, glowing softly against the darkness. See the bright central bulge, the graceful arms spiraling outward, the countless stars like grains of sand on a cosmic beach. You're looking at home, the largest home you have, the galaxy that contains everything you know, everything you've ever experienced, everyone you've ever met. All of it there in that glowing spiral. And now imagine descending back toward it, back toward one spiral arm among several, back toward one star among hundreds of billions, back toward a small blue world orbiting that star, back toward this room, this bed, this moment. Your home in every sense, on your planet, in your solar system, in your galaxy. Nested in layers of belonging, held gently by gravity, surrounded by the vast patient turning of cosmic structures. The galaxy will continue rotating through the night. The Earth will continue its orbit. The sun will continue burning, converting hydrogen to helium in its core, as it has for 4.6 billion years and will for 5 billion more. And you can rest. You can let go of awareness, let go of thought, let go of everything except the gentle drift into sleep. There's nothing you need to do, nothing you need to remember or figure out or solve. The galaxy takes care of itself. Your body takes care of itself. All you need to do is rest. Sleep is coming now. You can feel it at the edges, that soft, welcoming darkness. Don't resist it. Don't try to stay alert. Let it take you gently, like a wave lifting you and carrying you away from shore. You're safe. You're held. You're part of something vast and ancient and beautiful. And now you can rest, deeply and completely, carried through the night by the gentle rotation of home. Thank you for traveling through the Milky Way with me tonight. Thank you for being here, for listening, for letting these words and ideas wash over you like starlight. I hope you found some peace in this cosmic perspective. I hope your worries feel lighter now, held gently against the backdrop of billions of years and hundreds of billions of stars. I hope you felt your connection to something larger than yourself. The galaxy is always there, always turning, always patient. Whenever you need perspective, whenever you need to feel part of something vast and enduring, you can look up at the night sky, or simply close your eyes and remember. You are stardust. You are billions of atoms with billions of years of history, temporarily assembled into this brief, precious, miraculous pattern called you. And that's beautiful. Sleep well now. Rest deeply. Let the galaxy carry you through the night on its ancient rotation. Let the Earth cradle you as it orbits the sun. Let your body heal and restore itself as only sleep allows. Dream of stars if you dream at all. Dream of spiral arms and molecular clouds, of ancient light crossing space, of atoms cycling through endless transformations. Or dream of nothing at all, lost in the peaceful darkness of deep sleep. When you wake, the galaxy will still be here. The stars will still be shining, and you'll be part of it all, refreshed and restored. ready to experience another day in this brief, beautiful existence. Thank you for being here. Thank you for existing. Thank you for being a way the galaxy knows itself. Good night. Sleep well. Rest in the gentle embrace of cosmic time and vast distances and patient starlight. Good night.